It's been demonstrated many, many times now that things will disappear bottom up due to the angular resolution limit of your eye or the camera, whatever you're using to look at something. People have done experiments. They'll go to like a there's hardcore science behind it. So I do not accept that angular resolution cannot cause things to disappear bottom up. I do not accept that.
So, but could you explain the experiment again?
This is a diffraction limit example as an addendum to the angular resolution series. This observation involves the following. A Canon EOS 70D with the center of aperture at 40.5 millimeters. The iPhone 6s on a stack of paper such that the center of the aperture is also at 40.5 millimeters on a 26 millimeter stack of paper, and an LED flashlight which is 14 millimeters tall with a 7 millimeter light roughly in the middle. So in the upper right corner you see the Canon EOS 70D. I have standardized the top of the lens, so at 81 millimeters, and divided it in half into 40.5 millimeters for the center of aperture height. I then did the same thing with the iPhone 6s using a stack of paper and variable amounts of sheets of paper to get it to the same 40.5 height. And this ended up with a stack of paper roughly 26 millimeters underneath the iPhone with its case. The light was placed on the end of a hallway, and each tile on the floor was a square foot, and we calculated out 262 tiles or 262 feet to where the camera was placed for the observation. So again, light is placed on the floor at the end of the hallway, the two cameras 262 feet away, and the Canon EOS 70D is placed on the ground with the center of the aperture at 40.5 millimeters, and the iPhone 6s is placed on the 26 millimeter stack of paper next to the EOS 70D so that the center of aperture is also at 40.5 millimeters. Okay, here's the setup camera, our stack of paper. Our distant light source. You can see the light in the viewfinder right there. And we're going to set our camera down now. Right there. Missing. Right there. Missing. So, so from the series, we know that things get smaller with distance. I won't go through this part too much, but just recall that we have two rays intersecting through f1 in front and behind the lens to create an image on the back of the retina such that things get smaller with distance at a rate of doubling the distance, halving the size. We needed 2 rays to form a contextual image. With only 1 ray, images are not rendered. So the next part was small things disappear. So in order for an object to create an image, it must be larger than the angular resolution limit of the observer, such that the angle it creates between focal lengths f1 and f2 behind the lens is larger than theta in radians, equal to 1.22 lambda, which is the wavelength of light, divided by the diameter of the aperture. In general, theta can be assumed to be 1 arc minute at 0.02 degrees, which is a fairly standard rate, plus or minus a half arc minute on either side for most camera systems. Small things disappear with distance secondary to the compression rate within a given field of view was our third part. The disappearance rate of a setting object is determined by the observer position. The observer height sets the horizon distance, therefore the only aspect of an image that can vanish within a compressed field of view is the observer's height, or the observer's distance to the tangible surface, like a floor or a wall. Objects above and below the observer disappear when the object height h is less than d tan theta. If the object is within the observer's eye line, it will reach the vanishing line at a quicker rate within the compressed visual field than the opposing expanded visual field, at which point the object will vanish with further distance and set. So for calculations, the horizon distance is set at the observer height O, such that d equals the observer height divided by tangent theta. Doubling the observer height will double the horizon distance across the same angle using similar triangles. Secondly, objects of a particular size h completely within the compressed or expanded field of view disappear at distance equal to the object size divided by tangent theta, or they set into the vanishing line. Objects that are partly compressed or partly within compressed and expanded fields, like within your eye line, and move straight away from you, disappear at d equals the observer height divided by tangent theta, and then for the remaining object that is above your eye line at that point, then the distance is equal to the height of the object that is still visible minus the observer height divided by tangent theta, and all that will be covered in some upcoming rules of angular resolution. So, but within this example, we don't need to use all of those. We will, for our angular resolution limit, we'll assume a standard 1 arc minute of 0.02 degrees. This will standardize the expected horizon for the 2 cameras given equal aperture heights, such that a different disappearance rate will mean a different angular resolution limit theta. So we'll first get the horizon distance for the 2 40.5 millimeter or 1.59 inch observers, plugging in the observer height for 40 millimeters and a theta of 1 arc minute. Distance is equal to the observer height divided by tangent theta, or the horizon is 1.59 divided by tangent 0.02 at 379.6 feet. And you can see that relationship in the diagram below, which is explained in the series. So in the top, just recalling from the video, we had our iPhone 6s at a 40.5 millimeter height with the light missing. We raised the iPhone 6s above the 40.5 millimeter height to then visualize the light. And we also showed that the Canon EOS 70D was showing the light the whole way at 40.5 millimeters. So we will lose our observer height of 1.59 inches at a horizon distance of 379.6 feet, which is what we just calculated. So objects still visible above our eye line at that point will set with further distance. In this example, however, we see that we lost the light from the iPhone 6s with the smaller aperture at 262 feet and had to lift our camera to observe the light again. The Canon EOS 70D captured the image at this same distance and height. The effective observer height for the iPhone 6s compared to the Canon EOS 70D at this same distance would be the distance at which the object disappeared, 262 feet, for the iPhone times the tangent of theta, or the observer height equal to d tan theta, or 262 feet, tangent 1 arc minute equal to 1.10 inches, or 27.9 millimeters. In other words, the Canon EOS 70D has a 1.59 inch minus 1.10 inch, or roughly half an inch, or 31% better resolution. So if we assume the iPhone 6s has 1 arc minute of resolution at these wavelengths and aperture diameters, the Canon EOS D has an angular resolution that is 31% better, or roughly at 0.014 degrees. Since the wavelengths sent to each camera within the corridor are the same, the only variable left is the aperture diameter. So we can say that the iPhone 6s for this particular distance had an aperture diameter 31% smaller than the Canon EOS 70D. So once again, horizons are optical phenomenon, they are not physical curvature. Note that zoom did not bring the image back, but switching aperture sizes magnified the image by altering the horizon distance, and the image is now resolved according to the Rayleigh criteria. So that concludes this example, and as always, God bless you all.